Hello everyone, welcome back to the course on Introduction to Multi-Agent Systems. In today's lecture, we'll talk about the basics of algebraic graph theory. So let's get started. So let us start by reminding ourselves of what is the adjacency matrix. So let's try to understand that through some examples. Let us consider the graph, the path graph given in this form with the nodes. Now, the adjacency matrix of this graph looks like this. So, 1 shares an edge with 2, meaning the only non-zero entry in the first row is A12. The rest of the entries are 0, meaning there is no self loop, so A11 is 0, A12 is non-zero as 1 shares an edge with 2. Similarly, A13 and A14 are 0 because 1 does not share an edge with 3 and 4. In a similar manner, we can construct the rest of the matrix as well, and it will take this form. So, let us first fill in the entries which are going to be non-zero. So, the next non-zero entry in the second row would be A23 and the rest of the and we can also see that 2 shares an edge with 1 as well, meaning A21 is also non-zero. The rest are 0. Similarly, 3 shares an edge with 2 and 4. So, A32 and A34 are non-zero. And similarly, 4 shares an edge only with 3, meaning A43 is non-zero. The rest of the entries become equal to 0. Okay. So, this is how we construct the adjacency matrix of any given graph. Okay. Now, let us try to think of some general algebraic properties associated with the adjacency matrix of a graph or a digraph. A digraph is a directed graph. Okay. Let us consider a weighted digraph G with the adjacency matrix with an adjacency matrix A. So, then what are the properties that A always satisfies? So, the first one is, now every undirected G graph G always has an A matrix which is symmetric in nature. An example of it is the path graph shown here. Now, of course, the symmetric matrix associated with a digraph can also be symmetric in nature, but that is not in general true. Okay. Now, let us talk about another property associated with digraphs. So, let us first write here. So, here we have A equals A transpose. Now, for a weight balanced digraph G, so in a weight balanced digraph, the property that always holds is this. A transpose 1 n. So, what does this mean? if we focus on any ith row, then suppose we look at some ith row and the ith column as well, then the sum of edge weights along the column is equal to the sum of edge weights along the row, meaning the sum of weights of the incoming edges to the node is same as the sum of the outgoing edges from the node. So, this is what a weight balance digraph means. Okay. Now, is a weight balance digraph always symmetric in nature? So, I will not answer this question. This question is for you guys to try out. Let me write the question here. Please try to answer this question by yourselves. Okay. Now, let us look into some more properties associated with the adjacency matrix. Before that, let us look at a small example. Okay. Now, from the definitions that we know from before, we know that node 1 acts as a source node. And node 5 acts as a sink node. What is a source node? A source node is a node which only has outgoing edges and no incoming edges to it, and similarly a sink node is a node which only has incoming edges and no outgoing edges. Okay. So, are there any interesting properties that the nodes associated with sinks and sources in the adjacency satisfy? Let us look at that. So, let us try to write up the adjacency matrix of this particular digraph. There are 5 nodes. So, it will be a 5 cross 5 matrix, and so let us see, 1 has an outgoing edge only to 2. So, in the first row, the only non-zero entry is A12. And 2 has 2 edges to 3 and 4. So, three has to 5, 4 also has to 5. And 5 does not have any outgoing edges. So, what do we observe here? Let us see. Let us focus first on the source node. So, the source node is node number 1. If we see here, for node number 1, the first column is always 0 for a source node, meaning it does not have any incoming edges. So, if we only look at the adjacency matrix, how do we spot a source node without looking at the digraph? We simply check for completely 0 rows, columns. Every completely 0 column is a source node. Okay. Now again, let's look at the sink node and see if it satisfies any nice properties. Now the sink node is node number 5. Again, if you observe here, all of the entries of the columns of a sink node are completely 0, meaning that again, if we look at the adjacency matrix and if we look at rows which are completely zeros, then we know that those are the nodes associated, or those are the nodes which are the sinks of a digraph. Okay, so let's write it down. So of course, the assumption here is that there are no self loops associated, otherwise at least one of the entries become non-zero. So let's frame it. For the source node I. Similarly, the entries of the ith row or let's call it jth or the sink node j. So note that how are these properties useful? Now, in order to identify which is a sink node and a source node, we do not now need to look at the graph. We can simply look at the adjacency matrix and check for rows or columns which are completely zeros, which will directly lead us to the sources and sinks in the network or the graph. Now, let's look at some properties which are associated with the adjacency matrix of row stochastic matrices. Where do row stochastic matrices come up? So, we have talked about the de-Groot averaging model before, and we know that row stochastic matrix do come cropping up in these real world examples as well. So, let's check some properties associated with them. Okay. For any row stochastic adjacency matrix, say the following properties hold. First is all the entries of the matrix A are strictly non-negative. And the row sums add up to 1, which can be written in this manner. A1n simply represents is a vector whose every entry is nothing but the sums of all of the rows. This adds up to 1. Okay. So, these are the two properties that the adjacency matrix satisfies when it is row stochastic in nature. Similarly, what happens when the matrix is doubly stochastic? If it is doubly stochastic, it means that it is both row and column stochastic. So, just one more property gets added here. Let's write it. So, the additional property which holds in this case is that the column sums also add up to 1, meaning A transpose 1n is now also equal to 1. So, 3 properties hold for a doubly stochastic, this, and this. Okay. Now, let us look at some properties which are associated with the powers of the adjacency matrix and how exactly are they related to the walks in the graph. So, here we will focus only on adjacency matrices which are non-negative in nature. Okay, so let us see. Let us consider some digraph G. Then the following properties hold. So, there exists a directed walk of length 1. Now, what is a directed walk of length 1? It simply represents an edge in the graph. So, let us write it. A directed walk of length 1. Between any two nodes I and j. Now, as I said, a directed walk of length 1 is simply an edge. So, when do we say, like, what properties should the adjacency matrix satisfy? It simply means that there must exist an edge from I to j, meaning the entry Aij should be non-zero. So, let us write it. If Aij is not equal to, okay. So, which implies, so what should we observe here? We should observe that whenever we are talking about a walk of length 1, we need to look at the adjacency matrix. Now, let us say if we square the adjacency matrix, does it tell us any information about walks of length 2? For that matter, if we take a cube of the adjacency, does it now talk about walks of length 3 and so on? Does a to the power k give us any hint about walks of length k? Let us try to answer that question. Okay. Let us start with a simple case of a square and see, does a square actually talk about walks of length 2? Now, let us check that. So, what is the ijth entry of A square? It simply is the ijth entry of this product. Which is obtained actually by taking the ith row and the jth column. Let us write down their entries. AIN, and similarly this is ANJ. Now, both of them are the matrices A, and I have just written what is A square, and the ijth entry is simply equal to the product of the ith row and the jth column. So, let us write it out what this product looks like. A to j up to nj, in other words. Okay. So, let us now start assuming some properties about A square. Let me now say that the ijth entry of A square is greater than 0. So, notice that we are talking about non-negative matrices. So, whenever we say that Aij is not equal to 0, it is actually strictly greater than 0 as well. Okay. So, now let me make the same claim here. A square ij is greater than 0. What does it mean? It means that something at least, so these are all positive numbers. What it means that at least one of them is now not equal to 0. Okay. Now, let us let me write this now in the form of a summation. AIH, AHJ, where H varies from 1 to n. Now, at least one of the entries here, it is not equal to 0, meaning suppose let us assume that some pth entry here is not equal to 0. This implies at least one entry of the form AIP and APJ is greater than 0. Now, what does this imply? For this product to be greater than 0, it also implies that both of them are independently also greater than 0. What does this mean? It means that if I am now constructing or looking at the graph, it means that if I am starting at node I know that there is a path from I to P because AIP is greater than 0. I also know that there is a path from P to J, meaning APJ is greater than 0. So, what have I constructed in this process? I have constructed a directed walk from node I to node J, which now has a length equal to 2, meaning that A square ij being greater than 0 actually implies the existence of a walk of length equal to 2. And this logic can be extended to beyond, so that we can say that if we now raise A to the power k and look at the ijth entry here and say that it is greater than 0, then I can say with absolute certainty that there exists a directed walk of length k between nodes I and j. Okay, so these are very interesting properties. Why? Now, it says that in order to construct or in order to talk about walks within a network, it is sufficient to focus only on the adjacency matrix, and we can actually talk about the existence of a walk of any arbitrary length. Meaning, if I want to ask a question of whether a walk of length 100 exists, all that we need to do is plug in these numbers in some software or something, maybe MATLAB or somewhere, and then check if all of the entries are greater than 0 or which of the entries are greater than 0, and correspondingly I can tell whether walks of length 100 exist or not. And these properties can also help us in commenting on the connectivity between graphs. So, how can we use these notions to make more comments on the properties of the graph is something that we'll talk about in the next lecture. Now, let's look at some examples of how we can actually use the powers of the adjacency matrix. To begin with, let us consider the graph shown here. For this graph, let us fill in the entries which are given here. The first is, what are the walks of length 1? Let's see, the walks of length 1, there's one walk from 1 to 2, and there's another walk of length 1 from 2 to 3. Okay, so how many walks are there of length 2? Length 1, that's equal to 2. Correspondingly, let's look at the adjacency matrix. If we write up the adjacency matrix, we see that there are only 2 entries in the adjacency which are actually equal to, which are not equal to 0, implying that there are only 2 walks of length equal to 1. Okay. Now, let's look at walks of length 2. So, we see that there is only one walk which has a length of 2, that is from 1 to 2 to 3. Now, again coming back to a square, we will see that there will be only one entry here which is actually not equal to 0, that is equal to the entry a squared (1, 3) is greater than 0. So, notice that I actually did not calculate the entire matrix. All that I did was I checked for walks of length 1 and length 2. I made only those entries not equal to 0, and rest of the entries I straightforwardly made 0 because I know that such walks do not exist. For example, a 3 to 2, I know it is equal to 0 because when I come back to my graph here, I see that there is no walk from 2 to 3 of length 2, right? Okay. Similarly, let's look at the second example shown here. Again, which are the walks of length 1? We see that there are 3 walks, 2 to 1, 2 to 3 and 1 to 4. Again, we see that there will be only 3 entries in A which will be non-zero, corresponding to walks of length 1. Similarly, what are the walks of length 2? Again, there is just one walk which is equal to 2 to 1 to 4, meaning in A square, the entry 2 to 4 is the only entry which will be greater than 0, meaning this here will be equal to 1. Again, so just by observing the graph, the walks in the graph, the entries of a to the power k can actually be filled. Okay. Now, let us modify the same graph which is given here slightly and see what happens. Okay, let us look at another example. Okay. So again, how many walks are there of length 1? We see that there are 4 walks. Meaning, again, if I am trying to write A, then the entries 2 to 1 will be non-zero, 2 to 3 will be non-zero, 1 to 4 will be non-zero, and 3 to 4 will be non-zero. Rest of the entries in the adjacency are going to be equal to 0. Now, similarly, let us look at walks of length 2. How many walks are there of length 2? There are again 2 walks, 2 to 1 to 4, and the second walk is from 2 to 3 to 4. So, notice that between the nodes 2 and 4, there are actually 2 walks of length 2. So, in that case, what happens to A square? Meaning, if I had, let us say, let us first write this. So, 2 to 4 is, this entry is now non-zero, and the rest of the entries again are equal to 0. Okay. So, suppose we see that in this example, this entry is equal to 1. What should be the value of the entry A24 in this case? Sorry, this is A squared. Should it be equal to 2? Should it be equal to 3, or what should be the value of this entry? And what does this value signify? Now, so let us try to answer this question. What does this entry, what does the value of this entry signify? We know that if it is greater than 0, there exists a walk of that length, but does the value actually mean something, or when does the value actually mean something? So, this leads to the question of counting the number of walks in a graph. How do we count how many walks of length 2 exist? So, in this case actually, since this is not a weighted graph, a very simple thing happens. If we solve it completely, we will get this value to be equal to 2, and we see that there are actually only 2 walks of length 2, and the entry of A24 is also equal to 2. But now, suppose I had added some weights here. This entry would not have been equal to 2, meaning that in general, in a weighted graph, the entry of A square being greater than 0, while that implies the existence of a walk, the value of the entry does not really give us the number of walks. But if the matrix is actually a binary matrix, meaning the edge weights are simply equal to 1. So, meaning let us replace all of them by 1. In this case, the value of ijth entry of A square actually also gives us the number of walks of that particular length. So, let us try to summarize this result. How do we count the number of walks? Now, for a weighted digraph G with n nodes and some adjacency matrix A, we define a binary adjacency matrix A01 such that first every entry of A0 J1 is either 1 or 0. And Aij is equal to 1 only when there exists an edge between from I to j. So, notice that irrespective of the weights of the graph, we can always associate such a matrix with the graph, meaning we simply replace the weight with the value 1 and then construct the binary adjacency matrix. Now, if we have constructed the binary adjacency matrix, then we can say the following. And some positive integer or natural number k. What are the things that we can say? We can now say that a to the power a raised to the power k and the ijth entry of it, if it is greater than 0, we can definitely say that there exists a walk of length k from I to j. We can say that with certainty. Not only that, we can also say the following: the entry, so we should add 0 1 here, signifying the binary adjacency. Now, the entry A01 raised to the power kij equals the number of walks of length k from I to j. And the same we saw in the previous examples. For example, in example number 2, we were working with the binary adjacency matrix and we saw that the value of A2 to 4 of A square. So, A square signifies walks of length 2. We see that A2 to 4 is equal to 1, meaning there is just one walk of length 2. Similarly, when we modified the graph slightly by adding an edge from 3 to 4, we saw that the number of walks of length 2 increased from 1 to 2. And the same can be observed in the entry in the 2 to 4 entry of A square. Okay. So, with this we come to an end to this lecture. In the next lecture, we will start talking more about the graph theoretic properties associated with the adjacency matrix. Okay. Thank you.